This conference will now be recorded.
Okay, so gravity on a human scale, in terms of the objects that we're working with, it's not a significant player. On the other hand, we have also these nuclear forces that we've learned about in the 20th century. We have something called the weak nuclear force and the strong nuclear force, but they only operate at the subatomic levels. They're very, very tiny forces at this molecular level and the strong nuclear force at the subatomic level. Okay, so again, they're not things that impact us in real life. The only one of these forces, remote acting forces, that really impacts us at a human scale is electromagnetic radiation. That is something that is an energy that can affect us, that we can use, that we can work with, and so on and so forth. So you can watch the video, and that gives you a little bit more background on it. Okay, so that's one of the reasons why we're interested in it, because it can affect us, and we can use it usefully as an energy source. Okay, non-ionizing radiation is electromagnetic radiation with insufficient photon energy to ionize matter. In this definition, I think it came up on the exam even, so it's kind of a preview on one of the questions there if you haven't started it. The division between non-ionizing and ionizing radiation, if you look at the continuum of like the electromagnetic spectrum, generally when we start to talk about the energy levels that we need to ionize molecules or atoms, in other words, pull electrons off and ionize them, we're generally talking the high end of the ultraviolet range. Okay, so that makes sense, right? Because we know that that's the beginning of the point. No one ever talks about getting skin cancer or mutations associated with visible light in the visible light range, but certainly once we get into the UVB, UVC, UVB, and UVA range, we're getting up to energy levels that part of the electromagnetic spectrum and further up, higher in frequency and shorter in wavelength. Those higher energy wavelengths can ionize materials, atoms, and molecules. Okay, and they put the number at 12.4 electron volts. And they show, what do they show there? What instrument is that? Anybody familiar with that instrument? Anybody take the lab yet? You didn't take the lab yet. Okay, that's a photoionization detector. And what that does is, it's got a little pump on it. You see a little wand sticking out the end of it. It's sucking air into it. And you can be in an environment where this device has a little cell in it. And in that cell is a high energy ultraviolet light source. And there's a little cell in there, and it's constantly monitoring the conductivity across that cell of the air and the gases across that cell. And as air is being pulled in here, if it has organic molecules in it, okay, the bulb that's in there has sufficient energy to strip some of the electrons off of those organic compounds that might be in the air. And when it does that, it makes the gap, that area in that cell, it makes it conductive. The electrons are been removed, so you have positive particles, you have the electrons, so they now can move across that gap, across that cell. And you can tell how much of an organic is present in the air by how much you increase the conductivity in that cell. And it literally uses, say, a 12.5 electron volt lamp, a lamp that's capable of generating that amount of energy in order to do that. Now, they also have lower energy lamps like 10.5, and that are useful for a certain class of organic compounds. So I think 12.4 is a little bit above the range where you could start to see it, but it's certainly in that ultraviolet range where we start to see the changeover. Okay, so the many devices and tools and appliances that we use that emit non-ionizing radiation. First of all, radios, our phones, the antennas that broadcast to our radios, microwaves that broadcast to our phone broadcasting to the cell towers that this is connected to. This little phone array can generate enough energy to reach that cell tower and deliver information to it using microwaves, radar, lasers, and so on and so forth. All are sort of some sort of non-ionizing radiation. Lasers, what kind of ionizing radiation is a laser? Isn't that just light? Just light, right? Okay, so it's still not non-ionizing, but it's light. So we kind of like, I played down the issue of visible light, if it could be hazardous. Well, if you play with it enough, you can turn it into something hazardous. We're going to be talking about that in a little while. Here's another video that when you get a chance, you might want to go back to and watch. Basically, this is describing the relationship between the energy, the strength of a field, and it's describing it in terms of the quantity of charge that's generating, the quantity, the strength of the charge, and the distance from that moving from those moving electrons. And K is a constant, Coulomb's constant, for converting one from the other. So electric fields are produced by electric charges. Okay, magnetic fields are produced by magnets, but they're also produced by moving charges as well. Okay, they exist in a perpendicular to the flow of current. There's something called the right-hand rule. If you guys online can't really see this, but if you play those videos, you'll see this. But if you have current flowing through a wire, the magnetic field around that wire is coiled, is circular. If you take your hand, the magnetic field is in this direction as the current is moving in this direction. So if the current's moving in the other direction, the field's moving in the opposite direction. Okay, so we're continuously exposed. For instance, we have 60 hertz current that's connected to the wall here. So we have magnetic fields coming off of that. And that's an interesting one because it's constantly changing direction, that magnetic field, that current flow, okay, and the direction of the field. Okay, so people are continuously exposed to electromagnetic radiation as a result of this use of AC current. Here you go. Here's kind of a little bit of an image of where we're looking for that in terms of the magnetic field generated by current flowing through a wire. By the way, have you ever noticed that have you ever pulled open telephone wire or RJ, what is it, RJ32, the internet Ethernet wire? Have you ever opened them up? You ever notice that, like in telephone wire, it used to be 4 wires inside, like green, blue, red. You recall, you've seen that, I'm sure. And on RJ45s, I think it is. So that's the connector on Cat5 cable. If you open it up, you'll see 4 pairs of conductor. Each one of them is a data and a ground. Okay, a line that data is sent out and a ground right next to it. And there's 4 pairs of those, so there are 8 wires in there. If you look closely at the connector, you can see there's 8 little ports there. And they're standard, they're colored and so on and so forth a certain way. If you look closely at them, the wires are always twisted together. The ground and the other wires always twist together. It's called twisted pair. They do that on purpose. The reason why they do that is if you can imagine, if you have a signal going through a wire and you're sending data in the form of AC, it could be the current going back and forth. In the form of DC, where you're sending data, it's like +3 volts, no volts, +3 volts, no volts. It's these little spikes that you get going through that wires, and electrons go through it from 0 volts to +5 volts. So you get little pulses going through there. Well, if you're changing what's going on in that wire, that wire has a magnetic field in it. Right? And if there's change in that magnetic field, what's it doing to the wire next to it? It's inducing a current in the wire next to it. So if you run a wire long enough with 2 of them together, right next to each other in a straight line, what's going to happen is it's got that induction of current in the wire next to it is going to interfere with the signal that you're trying to send to the other end of that line. So they twist them together. So you're constantly making up for that by having the wire on one side for a little while and then the wire on the other side, and the wire on one side. So it negates, overall it negates, but you still have an issue with, you've heard that Cat5 is only good for whatever, 300 feet or 200 feet or something like that. And that's part of the reason, is because of the deterioration of the signal from those wires. Okay, so any of you guys network people that online that work with network systems and so on? I'm not, it takes a little while to get a response sometimes. First, I have to wake up. They have to come to, and then they have to type and so on and so forth. So I'm gonna move on. Hopefully, I'll get a response that see if anybody has ever worked with networking systems. Okay, so in terms of moving this idea, current and voltage into a more relatable kind of situation. No, I got a nope. Okay, good. Thank you. Voltage is correlated voltage. If you're looking at water lines, the corollary of voltage is the pressure that's in a water line. It's the amount of force that it's moving with. And current is the number of electrons that are moving, which is the corollary to that might be the amount of water that's moving through that line. Okay, so if you take a look at this, electric fields are produced by this force, this electromagnetic force, and magnetic fields are produced by the actual movement of the electrons. Okay, now electric and magnetic fields, they propagate out, but they act perpendicular to one another. So even though they're moving together, they're propagating out there. The actual waveforms are perpendicular to each other. This formula is basically saying that the power density, overall power density, is equal to the electromagnetic field, the electrical field times the magnetic field. Now, the other interesting thing about this is that there is this other issue of depending on the frequency and the wavelength of the electromagnetic field, the impact, the effective impact of the overall electromagnetic field, the combination of the power density, when we're at a short, when we have a low frequency source like 300 megahertz or less, this combination of magnetic and electric fields is hard to measure, is hard to quantify without measuring each individually. On the other hand, once we get to higher frequencies, then the field that the electromagnetic field that's generated, the electrical field that's generated far outweighs the magnetic field that we would deal with over short ranges. We'll see that. That's near versus far field. So near field, relationship between electric field and magnetic field is not constant, so you got to measure both. Far field, this is a constant relationship between the fields, and the inverse square law is applicable for far field. So we use a different method, different formulas for calculating the power density for far field regions where we're talking about more than 2 wavelengths from the source, and near field where it's less than 1 wavelength, and in between. Now this is important because if let me see, here we go. If you look at this, the relationship between the frequency and the wavelength. So if we have 60 hertz, right? So electromagnetic fields travel at the speed of light. So if we want to know what the wavelength is for 60 hertz, the speed of light is equal to the frequency times the wavelength. So if we want to know what the wavelength is for 60 hertz, well, 60 cycles per second. Anybody know? Oh, it's right here. The speed of light is 3 times 10 to the 8th meters per second. Okay, in air. Okay, and if we wanted to know how many meters the wavelength is for 60 cycle electricity, we would say, okay, 3 times 10 to the 8 is equal to the wavelength times 60. Divide 3 times 10 to the 8 by 60. We're talking more than 10 to the 6 meters. So the wavelength for 60 hertz 60 cycle or 60 hertz electricity wavelength's enormous, right? So we're with that low end of the spectrum, we're always dealing with this issue of measuring magnetic and electrical fields. It makes it more complicated, put it this way. But when we get up to the very high end, we're talking about very high frequencies. Well, then we're talking about at that point when we talk into more than 300 megahertz and into the gigahertz range, like cell phones and microwaves and so on and so forth. Well, then the wavelengths are so small at that point that we're only talking about fractions of a meter. So we only have to worry about the electrical field density. Okay, far field relationship. The electrical field strength is equal to the magnetic field strength times 377. So we really don't have to bother with the magnetic field strength. Okay, so far field power density. We'll move on with it. We'll return to that. We're going to wind up working on a couple of problems that'll involve that. Okay, possible health effects, induced cut. Well, you can imagine that if you have all these fields running around, and these fields can induce currents as we move around, as they move through us, and so on and so forth. The concern then is that maybe these things can produce a significant amount of electrical currents in our bodies, that they can have some health effects on us. In an environment where there's a very large magnetic field or electromagnetic field, we could actually maybe sense small shocks and stuff like that. They might maybe the currents might exceed levels that might exceed normal levels in our body. So to put it into perspective, though, rarely in any kind of environment that we would ever get into would these electric fields induce currents that would be anywhere near what your heart uses or what your brain uses and so on inside of your body. But they can induce currents inside your body. And there is some concern that these various effects, these electromagnetic effects, these inductions of current, and so on and so forth, can increase risk for a lot of longer term illnesses. Okay, right now, there's a lot of speculation about this. There's no hard evidence that any of these things. You've heard anecdotal situations where people say, "Oh, well, this person would always put his phone to the right side of his head and wound up with brain cancer or tumor in that area, same area used, and so on and so forth." Unfortunately, those are not experimental studies, and certainly there's a lot of coincidence that can be going on with that kind of stuff. But there's no hard evidence at this stage, unless somebody online or you guys can find some study that maybe is a little bit more suggestive or something like that. No good hard evidence that the normal kinds of magnetic fields that we would be exposed to, like from our phones, causes cancer or other ill effects. You can feel them though. I mean, this is a certain amount of energy, right? And they get hot. So, it's like putting a light bulb next to your head, right? So you can imagine if they're generating a lot of heat, they're generating a lot of a field that's pretty sizable. Any of you guys avoid putting it up to your ear? Just use a speaker or something like that, or a microphone because of that? No? Okay. I know people that do that. They won't put them against their head. Okay. Magnetic fields decrease with distance. Of course, what is this going to be? It's going to be the inverse square law, just like any other kind of form of energy. And as you double the distance, you quarter the amount of energy. So these are threshold limit values for magnetic fields that are below 30 kilohertz. And so, for instance, the kind of fields that we would get off of our electrical system in our home, for instance, and from 1 to 300 hertz, that would be the range of AC current in a home would be 60 hertz or 60 cycles. So the limit for whole body exposure is 60 divided by the frequency, which would be 60. So it's basically 1 millitesla or 10,000 milligauss, right? A Tesla is the basic measurement for measuring the amount of energy that we're concerned about. Okay, and there's some parts of the body that might be more sensitive or less sensitive. Okay, and then as we change ranges, as we change frequencies, well, then there may be reasons why within those ranges that an exposure is more significant. Like you can see 300 to 30 kilohertz is more significant than 1 to 300 hertz, and then the higher frequencies. Okay, so beginning from calculate the TLV for individuals living under power lines in the United Kingdom. The electrical frequency is 50. Well, we know that's 50 hertz, right? We travel. So in the United States, the whole body exposure for 1 to 300 hertz is 1 millitesla. So in the UK, that would be, instead of 60 over 60 over frequency of 60, be 60 over frequency of 50. So that would be 20% more than this. In other words, 1.2 teslas. Okay, I'm not going to bother to write that out. Make sense to you? In other words, here the whole body exposure is 60 divided by the frequency. So in the United States, that's 1 millitesla. In Europe, in Great Britain, the frequency of electricity is 50 cycles, so it'd be 60 over 50 would be 1.2 millitesla is the exposure limit. Would be the exposure limit if they use the same standard as the United States. Oh, there it is right there. Thank you very much. Okay. The exposures can vary dramatically according to what kind of occupation you have, where you work, what kind of equipment you work with, and so on and so forth. Take a look at this one that most shows some of the most dramatic exposures. Sewing machine operator in a garment factory, because they're working right next to that motor and the other devices that operate while they're working at 60 cycle electromagnetic radiation. Government office worker. Okay, and there's a spike where he was spending a lot of time next to a copy machine and so on. Okay, so here's some typical exposures for other occupations.
So TLVs are pointing to ACDI8, right?
That's a good question. Yes, because I don't think OSHA has a specific standard, but NIOSH has recommended standards. I think they're basically the if it's TLV, it's definitely ACGIH. Okay, electrical fields. Oops, let me go back to that. Okay, ceiling for frequencies and a ceiling of for where we're dealing with higher frequencies like 3 to 30 kilohertz. We're talking about a somewhat more less generous exposure limits. Static magnetic fields have a frequency of 0. There's nothing moving. Okay, but if they're big enough magnetic field, they can have effects on certain kinds of body functions. Okay, static electrical field sources, MRIs and nuclear MRIs, superconducting magnets, televisions, computer monitors, and some work sites as well. Okay, for TLVs for static magnetic fields, whole body is 2 teslas, quite a bit more than the other exposure was. MRI emits upwards of 30,000 Gauss. Okay, anybody remember, did you notice what the conversion between Gauss and Tesla was? Okay, a millitesla is 10,000 Gauss. So how many milliteslas is 30,000 Gauss? It's 3 milliteslas, right? So if the limit is 2 teslas, right, for that static magnetic field, we have 3 teslas. So we're above the limit for that MRI machine. There you go. 30,000 Gauss and 1 Tesla per 10,000 Gauss. 3 teslas, we just saw that for a static magnetic field like an MRI, that the worker exposure limit is 2 Teslas. He's overexposed. Okay, so let me pass through. You guys can go back and take a look at this. How are we doing on time? Okay, terrible, of course. Radio frequency, main effective exposure to radio frequency microwave fields is heating of body tissues. How do we know that? How do we know that when we're up in that range, that heating of body tissues is like an important effect of that range? Well, microwaves, MW microwaves, right? No one doesn't have a microwave at this stage, right? So we know we put something in there and we get a result. But by the way, why do microwaves heat stuff up? I mean, why does you put something in there and it heats it up? What's going on in there? You're creating microwave radiation. You're creating an alternating field, a magnetic field that changes all the time, changes millions of times, hundreds of millions of times per second. Well, what's going on in there? Well, a lot of the things that we want to cook have got a molecule in them which is polar. It has a positive end and a negative end. What am I talking about? Water, exactly. So you put a piece of meat in there, it's full of water. Put your teacup in there, it's full of water. And what happens is that the microwave induces these alternating fields that vibrate those water molecules so quickly and so much that they heat up. There's a significant amount of heating. So really, in most cases, when you put food in there and it heats it up, it's mostly because it's heating. It's producing heat by moving those water molecules. Okay, so that's why you can also put stuff in here that doesn't heat up at all. You have microwave plates, you throw it in there, and it don't get warm at all. Okay, there's a video you can watch on water and potential to heat human tissue and stuff like that. Problem with that is that if you get too close to that microwave radiation that the device is creating, then you can cook yourself. Right? Now, how do we prevent that from happening? Well, that microwave is shielded. That microwave is enclosed in a metal cabinet that keeps those microwaves from escaping. But you need a little window to look in there to see what's going on in there, right? So you have a window in the front. How come you're not affected by those microwaves when you have that? You can actually look in there, right? So you know it's not completely shielded. The holes, the pattern of holes in there are specifically designed to allow you to look in, let visible light go in and out, but prevent that specific range of wavelengths that it's producing, a magnetic field that it's producing from escaping. Okay, so how do we know that it's not escaping? We got a meter. We actually have a meter here you can use. See, this is what happens when you stay home. You don't get to play with the toys. Okay, take that. Let me show you what this is, first of all. This is a microwave oven survey meter. It's basically measuring magnetic fields. And if you look on here, there's a little gauge on here that says milliwatts per centimeter squared. That's our basic measurement for electromagnetic fields up in that range. Yes?
At my work, I have someone that has complained about the microwave in there. So I would use that.
Yeah, you would use this, literally use this. And basically what you do is you take it in an area where you don't have a lot of electromagnetic radiation, you zero it. There's a little gauge over here to zero it, right? And then you take it to the microwave, turn it on, and press this button and look around the edges and the openings and so on and so forth. See if you can detect any microwave radiation. And based on how far away you are, you can tell what the power density of that microwave radiation is using this device. There's a cup in here to fill with water. Stick it in there so that you can test it while it's under load. In other words, simulate somebody actually cooking something in there rather than operating it empty, which might be a different environment than somebody working. So you fill this up, you put it in there. Not only that, but then you can run it for a while, and you got a thermometer over here so you can check to see how much it's warmed up, so you can see how much power it's generating. Is it really a 900-watt microwave or not? Well, it might have been when they first started putting them out. You don't know how well they managed to shield these things, or over time if the door gets damaged, if it's leaking or something like that. Certainly, if it's old Or if it's been damaged, it fell on the floor or something like that, it might be worth checking, right? Because you heat certain parts of your body, you get a real problem. Like for instance, your eye, your cornea, your lens are very sensitive to heating. So you could literally, damage your cornea from overheating. Yes.
So the goal is when you use this device in front of a microwave, you should not be reading.
Right, exactly right. Or if you're reading anything, it should be below whatever the standard is for exposure, below the TLV.
How much are those machines?
What's that?
How much are those?
I think you could probably buy them for a few $100. I would imagine, depending on how expensive it is, a few $100 might not buy you a lab grade, measure. Yeah, we're going to try and look around. Yeah, I haven't. Now, let me tell you something interesting. For a while there was a meme on the internet, right, that said, if you want to check whether your microwave is shielded correctly, put your phone inside the microwave and call it from another phone. Okay. And you want to know something? I've had people try that. Sometimes it works and sometimes it doesn't work, right? It's not reliable though. Why is it not reliable? Because the frequency, the wavelength, the frequency that this is operating at, 2 gigahertz or 2.5 gigahertz, whatever it is, right? Whatever that frequency is, may not be the same as what your microwave is operating at. So it may not be shielded correctly for the phone. So just because your phone rings in there doesn't mean that microwaves are getting out of it, right? So, but if you put it in there and you can't call it, it's probably working pretty well for your phone. Perhaps the frequency is closer than other microwaves to the frequency that your phone is using to communicate. So you can give that a try. If somebody comes, turns that microwave on and kills your phone, don't complain to me, okay? I never told you to do it. You guys are on that. I'm getting rid of this. You want to give it a try? If you can get her to open the door, yeah. It's locked, but I don't have a card with me. But yeah, if you want to take, I'll tell you what, let's take a quick break. And let's try the microwave. Okay, so we're going to give that a try, guys. We'll be right back. High frequency, high energy, exactly. As you get up in the spectrum, as you get the higher frequency, and of course, look, the electromagnetic radiation, look what's at the far end of it. Gamma rays, for instance, really high energy and really capable of ionizing. And again, we're at the borderline of this. We're at microwave, we're getting up into those frequencies where you start to see enough energy in these things to actually cause it to ionize. We'll be right back. Okay, we'll bring this with us. We fill it up with water. Huh?
Keep it going.
Yeah, let's go. Let's see if we can get into that room. Give it a try. Thank you. too bad. I was hoping maybe we catch what he could do that. Yes, there's no response at all. Now, unfortunately, I'll see if I can find something that'll respond to that I can bring in. We can give it a try. The other thing, I don't have another meter to measure other frequencies, right? So for instance, maybe, our cell phone. What I do have is something that'll measure the intensity of the light in here. Okay, so, which is electromagnetic radiation, right? So it's basically, this is a device that's measuring the intensity of the electromagnetic radiation in the visible spectrum. And you can actually tell it whether you want to work with fluorescent lights, I don't see incandescent lights. I don't think it has LEDs on here. These are fluorescents for the most part. Here, you guys can give it a try.
Intensity of the light?
Yeah, the intensity of light in foot candles or in lux. So another, if you really do intensive environmental surveys in a building, so an indoor air survey or something like this, maybe you don't just do, air quality, mold, CO2 levels. Maybe you also check lighting levels. Maybe you also check noise levels and stuff like that. So, I mean,
somebody playing with the light.
yeah, because that has an impact. So if it's too bright or not bright enough, that's going to affect productivity as well, right? In some cases, it might be a hazard if they're working, if they have to do fine work, and they make mistakes and stuff like that. Okay, so yeah, you can give that a try. You can actually measure the level of light. Okay, and the way that it works is that you put that little cover on there and you zero it. And then you take the cover off and you can actually make measurements. And you're supposed to choose, there's 4 choices there for the type of light, whether it's incandescent or fluorescent or, yeah, these are fluorescents. We also have, I guess those are halogens or something that are up in those little things here.
Is there a way to measure unknown light, or do you have to know the type of light?
That's kind of like, this is not really very sophisticated. So you're just kind of, it's assuming that if you have fluorescent lights or you have other kinds of lights, they're going to generate light in a certain range of wavelengths, and it kind of averages them. So, I mean, you could probably have much more sophisticated ones where you actually can, key into a certain wavelength or something like that. Frequency.
For example, if you walk into a gymnasium.
Yeah. Oh, there's standards for that. Yes, there's standards for the light level. Yeah, matter of fact, hang on a second. I might have something in one of these PowerPoints. Yeah, RF exposure. Yeah, there are standards. Maybe in the next PowerPoint. Yeah, here you go. iPhone, the SARs. I'm trying to think of. I'm having a senior moment, but it's basically the biological impact of the exposure. So kind of like quality factor when we're talking about radiation, not just like the amount of radiation that's being caused that you're exposed to. So this is the number of watts per kilogram of head and body effect that you have from radiation from iPhone 8s. Okay, and so basically what they do is they simulate in a lab a head and put a phone next to it, and they actually take measurements to see how much radiation that head is exposed to per kilogram of head, I guess, for want of a better term. Somebody asked me when assignment 5 is due. I didn't put a due date on it yet. It's going to be done, say, a week after the exam is due. So the exam is due December 1st, so figure December 8th will be when or December 8th or the next Thursday after that, like the 10th or something like that. So you don't have to worry about it until the exam is done. Okay, RF exposure, radio frequency exposure. So radio frequency, we're talking about higher frequency, lower, shorter wavelengths, 100 megahertz, 300 megahertz, your favorite radio station, right? And then up into the gigahertz range when you talk about these higher frequencies. And in that range, then the energy levels that we're talking about are mostly the electrical field, generated, and the magnetic fields are relatively minor compared to them, so we don't wind up measuring them separately. So here's an exposure guideline for, and remember we mentioned that within a certain range, like within certain ranges, that the biological effects of these exposures are greater or less. So you can see in this middle range, if we're talking about 100 megahertz or from 100 megahertz to 1,000 megahertz, we're talking about exposures that are the maximum exposures are lower than you would want in other ranges and other frequencies. You also notice that the relative effect of the magnetic field goes down as you go up in frequency. So that's when we wind up, the power density is basically measured by measuring the electrical field. Okay, power, some more information on typical power densities associated with different devices, phones and microwaves and so on and so forth. 5,000 microwatts per centimeter squared at 5 centimeters. That's the standard for a microwave. What did this device say? What was the measurement on that device? Do I have it back here? Somebody, is it up here? No, the this one. Do I have that? What did I do with it? Hang on a second here. It's in here. So the range, the scale goes from 0 to 5 milliwatts. And the standard is that we should not be able to read 5 microwatts at 5 centimeters, 2 inches from the microwave oven. So 5 microwatts is 5 milliwatts. So this is literally, there's a scale in here that says 0 to 5, and then it has a red bar. So literally that 5 is that 5 is the highest you should read at 2 centimeters ever from a microwave. We didn't read anything from that microwave that was operating in there, right? So it's not 0. Typical power density exposure. Actually, it's saying that that's a typical power density exposure from a microwave, and we didn't read anything like that. So maybe since that chart was made up, they've gotten better at shielding these things. Okay, radio frequency, micro frequency exposed, administrative, shielding, personal protective equipment, training, and so on and so forth. We'll get into that a little bit more in the next PowerPoint. Infrared radiation. We have in infrared radiation. We have UVA, UVB, UVC, and of course, UVA is the highest frequency. UVC is the lowest frequency. So the UVA is like the most energetic, and that's the one, UVB and UVA are the ones that are associated with effects like cataracts, like skin cancer, and so on and so forth, because they have more energy. They penetrate more. They're more likely to cause cellular damage than UVC. And in fact, I think they, don't they sell now that like if you buy a pair of sunglasses, they specifically will say it's good for UVA or UVB or something like that. And I think the more expensive ones will say that they're effective for UVB. Okay, UVA sources, the near infrared is the sun. You have other lamp sources and so on and so forth, like black lights, right? That's a incandescent source of ultraviolet light. And certain lasers operate in the ultraviolet light spectrum as well. Okay, laser hazards. Here's a video on laser hazards that when you get a chance, you might take a look at as well. Light amplification by stimulated emission of radiation. Basically, what they do is they stimulate a substance which produces, they electrically stimulate a material that releases photons when it's activated. So these photons, like for instance, if they have the specific material that they're using, like CO2 or some other material, those photons are associated with certain specific wavelength. And what they do is that they use a series of mirrors, so that as they produce this specific wavelength of light, depending on the material, ruby or whatever material they're using to produce it. That light that light bounces off the mirrors that they set up at specific distances, bounces off, reflects, so as they're continuing to produce the light from the source, bounces back and forth at the same frequency, so that the waves are additive. They're coherent. They're timed so that they are actually in sync with one another. So as what happens is, as this light is produced, the amplitude of the wave is increased because they're in sync. And eventually, when it builds up enough energy, it passes through the mirror. It's kind of a semi-permeable mirror. It builds up enough energy, it passes through the mirror, and you can beam it at things. One of the properties of this kind of light is that it's extremely coherent. It doesn't spread out like your flashlight does. So you can point it, and depending on what kind of material you use to generate it, what kind of how you amplified it, it can go very, very. It can be very, very powerful. You can cut metal with some of them, or you can use lower energy ones that just uses pointers that are relatively innocuous. But the light is extremely coherent, so you can literally beam that light miles away and it will not have spread out. It'll still be a pencil thin line of light instead of spreading out. So you don't lose the intensity of that light. And in fact, I think on the first Apollo mission, they sent, on the first lunar landing mission, they set up mirrors on the moon so they could beam lasers at it and time how long it took the laser light to reach the mirror and bounce back, so they could get a more accurate measurement of the distance from the Earth to the moon. Can cell phones and that's a good question. There is a little magnet that's inside your earpod, like your little earbud, and there's also some RF radiation from it if you're using Bluetooth, right? So in other words, you have that little thing you put in your ear is going to have Bluetooth, and it's also going to have a little magnet in it that's being used to create the sound that you hear, right? So there's a certain amount of electromagnetic radiation, but it's certainly not the level of intensity that you would get if you had the phone up against your head, because now you're not dealing with the level of energy that you need to make a tiny bit of a sound in your ear, and you don't have to. They last. The batteries in a little tiny things last a long time, so it can't be using much energy. But your phone has to produce enough electromagnetic radiation in the form of microwaves to reach a cell phone tower that could be 1,000 feet away, could be 2,000 feet away, right? And to operate all day, while you're using it, right? So my guess is that there's a certain amount of radio frequency radiation associated with them, but I don't think it's anywhere near the power density that you would be dealing with holding the cell phone next to your head. And that's not to say that that's anything bad is going to happen to you by holding the cell phone against your head. We don't have any evidence of that yet. Notice I said yet. Okay, so we have no evidence of that. Okay, continuous two sides of lasers: continuous wave lasers and pulsed lasers. Okay, clearly that just difference in the way that they operate. Okay, laser radiation can be described by these units: watts per centimeter squared and joules per centimeter squared. Okay, now watts per centimeter squared, that's a certain amount of power over acting over a certain area. Joules per centimeter squared, joules per second is the same thing as watts. Okay, so keep that in mind. Joules per centimeter squared pulse exposure. 1 watt is just 1 joule per second. Okay, so that they're really the same units, right? Except that joules is the action over a period of time. So if it's pulse, and a very short pulse, doesn't make sense to reterm it joules per second anymore, right? Or watts. Watts is for continuous exposure. Similarly, you could just say joules per second per centimeter squared for continuous exposure, but for pulse exposure, just joules per centimeter squared. Okay, the lasers are also described by their wavelength, depending on the material that they use to create it, UV, IR, and visible. Okay, here's some several laser media, common ones, ruby, neod, I'm never going to pronounce it. YAG. YAG is the other material that's involved. I can't think of the top of my head what it is, but gallium, maybe. We'll see it maybe in a future slide. CO2, and based on the amount of energy that they put out and the type of wavelength it is, you would use it for different kinds of things. Helium neons, that little red light that you see at the grocery checkout counter, they're also used in DVDs and so on. They're also used in construction. So you have to go out and buy one of those laser levels. Nowadays, you hang pictures. You go out to Home Depot, you buy a laser level, and that laser level you set up on a stand, and you can just it spins, and that little red dot turns into a line that's perfectly level around the room. So you can line up all the pictures you're hanging up. They use them in construction now all the time. Years ago, you would level the foundation by using a big long plastic tube and filling it with water, putting it one end and the other end, see if the levels are the same. Nowadays, you use lasers to do that. Okay, and again, they're usually helium neon lasers, low power, but they will come with, the ones that you use because you can literally, they wind up, like looking. Remember, distance has something to do with this. You literally could wind up just winding up, pointing this in your eye. They do come with protective equipment. They come with filtering glasses that you can use that are specific to the wavelength of the light that's being produced by the laser. We're going to talk about them, and have different densities that these glasses. So if you have a very dangerous laser, it's going to be specific for the wavelength of the light that you have, and the density of it, the filtering effect, will be higher for something that's more dangerous. You can get retinal burns, photochemical injuries, in other words, burns, lens-related damage, corneal damage. Again, your lens and your cornea are specifically sensitive, particularly interested to heat. Okay. Lasers, skin penetration, UV type, like the neon ones, don't penetrate very much. The UV invisible don't penetrate very much, and infrared penetrate a bit more. You know that there's controversy about using these higher power pointers for which are used, have a lot of purposes. They're popular among astronomers. Everybody knows somebody that's really into astronomy. If you go to a class, if you've ever taken an astronomy class, it would not be unusual for you to go out with the instructor, and in order to point out the look, you can't hold everybody's head and point them towards Orion's belt. However, if you have a high power laser, you can point to stars like Betelgeuse or something like that. You can point to the star, and everybody that's watching can see that strong laser go out and follow it from several angles, follow it to the place where he's pointing in the sky. So they're popular for applications like that, but they have to be pretty strong to do that. Your little pointer that would put a red dot on a blackboard or something like that in a classroom is not going to be anywhere near powerful enough for you to see a coherent beam going off into the sky. So they're relatively higher power. They limit legally the power that you can buy, but they have the potential for disrupting airplane traffic, for instance, helicopter and airplane traffic, because among other things, even if they're not strong enough to actually cause eye damage, they are strong enough to temporarily blind the pilot or cause him to have visual distortion for a little while after he's been exposed to it. Okay, and these are the various kinds of classes of lasers and the hazards that they can produce. 3B, 4, those are typically the levels that are used in laboratories and that are restricted use that you can't typically buy over the counter. But the lower level ones, like class 1, class 1M, that you would use as a pointer, for instance, in a classroom, they're particularly, they are relatively safe. Okay, laser warnings. Ancillary hazards. Some of these laboratory grade lasers, may use high voltage power sources. So you have explosion hazards, you got shocking hazards, and so on and so forth. You use them for cutting metals and for etching and so on and so forth. You have that you've seen schools now are using in places. It's like CNC type devices where you can actually cut out wood and patterns and stuff like that using a laser, and you can have fire hazards. You can have, depending on the material that you're cutting with them, you can have hazardous gases produced as well. Okay, here's laser standards. This is the maximum potential exposure in watts per centimeter squared, and this is graded by the laser type and the time of exposure. So if you have a CO2 laser, then you can't be maximum level you can be exposed to is 100 times 10 to the minus third, or in other words, 0.1 watts per centimeter squared over a 10-second exposure period, and a different exposure for 30,000 seconds for longer exposure. Actually, they're both the same level. Interesting, right? So helium neon, for instance. Okay, that's a higher exposure limit. And this is ANSI. Okay, nominal hazard zone. So it describes the space within which the level of direct reflected or scattered radiation exceeds the maximum potential exposure. So nominal hazard zone is the area that's close enough to the laser that you're exposed to more than the maximum potential exposure. Okay, well, you're going to use some of these. Okay, and here is and nominal hazard zone, NHC, and here is the nominal hazard zone, for various lasers. And now you can have eye protection. The eye protection has to be specific to the wavelength of light for the laser that you're working with, and the amount of energy that's in that light. And that determines the density, or basically a form of the protection factor for the material that's in those lenses. So the optical density, very much like when we were talking about noise and protective factor for noise. Okay, the optical density is equal to the logarithm of the initial beam intensity over the final beam intensity. The bottom is the final beam intensity. So we can do a quick problem there, I think. Calculate the optical density needed to protect the worker from a direct beam exposure to 0.51 micrometer argon laser for 600 seconds. Okay, so the wavelength is in micrometers, which is 0.154. Okay, and the exposure time is 600 seconds. So this is our maximum exposure limit, right? That's 16.7 times 10 to the minus 6 watts per centimeter squared. Okay, so we need to know what optical density that we need to get one that's 0.14. Let's see, which is operating at 13 watts per centimeters square down to this level. Okay, and okay, so here we go. So we have 16.7 times 10 to the minus 6 is what we wanted down to, and 13 is the number of watts per centimeter squared. That is the power level of the device. So the logarithm of this fraction is equal to 5.9. So we need glasses for this specific laser that has an optical density of at least 5.9. So we can go to a catalog, and we can go for an argon laser, which this was. We can go down here and we can pick out any of these protective lenses, filters, that are specific for argon lasers that have a protective factor of at least 6, right? So, and in fact, all of them are 7+. So, and in fact, if this were an actual link to this page, you can actually click on that and see the catalog information on that those particular protective lenses. And notice that they're all different. Some of them are protective for different kinds of lasers, right? For several different kinds of lasers, and some of them only have a protection factor of 4, for instance. But it'd have to be specific for those devices. Okay. Okay. So laser control measures. Okay, and of course, other control measures are important. Also, administrative control measures, preventing access to these lasers, confining the beam paths to optical tables, and minimizing stray beams. One of the hazards of these are coherent light, so they can bounce off things, they can reflect off things, and wind up exposing you by surprise. That's why you want to wear the protective equipment all the time when you're working around them, because there's a number of ways that by diffusion or dispersion or by reflection that you could be exposed to these things inadvertently. Okay, enclosures, very high powered lasers. You want to have enclosures so that you're not inadvertently exposed to them when they're operating. Ultraviolet wavelengths for these devices, 180 to 400 nanometers. UV radiation is in these 3 ranges. And the main concern is 200 to 315 nanometers because they are in what's called the actinic range. They're capable of causing photochemical reactions. So for instance, like burning your skin or causing reactions in your eyes and so on and so forth. Okay, UV health effects, again, skin cancer, and so on. You can go through some of these. There are benefits to UV radiation, UVA particularly, because that's how we generate most of our vitamin A. Anybody here besides me on vitamin D supplements? That's a big thing now, right? Yeah. If you get tested for it, I'm not sure what it does. I think it might be some cardiovascular effects or some neurological effects or something like that if you have deficiencies in it, right? But at any rate, as you get older, your ability for your body to produce its own vitamin D from exposure to light, or if you don't get much exposure to light, if you're in areas where, if you're Scandinavian or something like that, then you can be chronically deficient in vitamin D. So it's not unusual. This is one of those things that half the people I know at my age range are taking statins and taking vitamin D. It's kind of like standard. It comes with the territory. Okay, exposure to ultraviolet radiation concurrently with exposure to various chemicals can have synergetic effects, certain drugs and so on and so forth. And we know that's true. You take medications and a lot of them will have warnings about exposure, sun exposure, and so on and so forth. Synergetic effects with sun exposure. It's very much the same with other UV exposure. Okay, flow chart. Okay. Okay, so the effective radiation, in other words, the effect of radiation on your body in watts per square centimeter, in other words, the effective delivery of the energy associated with energy in this range, 180 to 400 nanometers, in other words, in the upper UVR range, is equal to the center of the wavelength, the amount of energy that's at the center of the wavelength. Remember, a lot of these exposures are not a single wavelength. They're a band within a band. It's equal to the center of the wavelength, the strength or effectiveness at that center wavelength, and how spread out that wavelength is, how broad that wavelength is. So the threshold limit value for broadband UVR is for various different wavelengths. For instance, for 225 nanometers is let's see, 2 millijoules per centimeter squared, 2 times 10, 20 millijoules per centimeter squared, and that's a relative spectral effectiveness of 0.150. Okay, calculating TLV for broadband UVR, calculating exposure time. How much, given these exposure limits, these threshold limit values, how much of a broadband UVR can you be exposed to over a period of time before you exceed these limits? Okay, so the time is equal to the number of joules per centimeter, 0.03 joules per centimeter squared over the effective limit. In other words, whatever this limit is in joules per second. Oh, I'm sorry. Okay, so the maximum of time that you can be exposed to is the threshold limit value over the energy level of energy that's being produced. Okay, so 26 medical students were exposed germicidal UV spray for 90 minutes during the autopsy demonstration. Timer was intended to disinfect the area at night when the suite was unoccupied, malfunctioned. So instead of disinfecting the suite, the surgical suite, it disinfected the students. All students reported both eye and skin symptoms, exposure assessment, which would certainly suggest that they were overexposed. An exposure assessment showed that the lamps produced 0.15 milliwatts per centimeter squared. How long could the students be exposed to the lamps and stay within that limit? Okay, so first of all, number one, the amount of energy that we're talking about from that lamp was 0.14 milliwatts per centimeter squared. Okay, we're going to turn that into watts per centimeter squared because that's the units for the TLV. Okay, so that's equal to 0.0014 watts per centimeter. Okay, and then we're going to put that down here in the bottom. That's the strength of the actual exposure, the source, and the limit is 0.6 joules per centimeter squared. Joules is watts is joules per second. Watts is joules per second. You can convert this into joules per centimeter squared second. So what's going to happen is that joules is going to cancel with joules, centimeter squared is going to cancel with centimeter squared. Seconds is going to be left, going to come up to the top. So the answer is going to be in seconds. So the units are right. So let's take a look at that. What was the frequency? 254 nanometers. 254 nanometers. And here is our TLV is, where'd my mouse go? 6.0 times 10 to the 1. And that was our source for, that's millijoules. Is that millijoules? Joules per meter squared, excuse me, that's joules per meter squared, right? And if you take joules per meter squared and convert it into joules per centimeter, it's gonna that's 60 joules per meter squared is equivalent to 0.06 joules per centimeter squared. Okay, and that we divide the same units now, joules per second, cancels out, you wind up with 42 seconds. In other words, the amount, the threshold limit value for that level of exposure was only 42 seconds. How long were they exposed? 90 minutes. So it's not surprising that they would have some residual effects. Okay. Corneal light exposures during at this higher range, 350 to 400 nanometers. Ion corneal exposure guidelines protect lens and retina. Shouldn't be exposed to more than 1 milliwatt per centimeter squared. Okay, let me move on from this. And how are we doing on time now? Are we done? No, we got a little bit more time. So I'm going to only go on for just a little bit longer. Now this is on these other PowerPoint is on Blackboard, and this one has some actual examples. This again, we're going back to lasers, monochromatic light, only one wavelength, and it's amplified. Normal light, like light coming out of a light bulb, you'll notice is polychromatic. In other words, it'll actually show you the bandwidth of the light when you go by a light bulb, to demonstrate that it simulates. It's very white. It combines all the different frequencies, so it's a kind of white light, or it's a natural light, yellowish natural light, outdoor light, and so on and so forth. It's directional, it's coherent, it's directional, and so on. That's the property of lasers. Differently, you might want to go through a little bit more better description of the different classes of lasers. And laser reflections and exposure. In other words, exposure is not just again directly in the beam, but it's also indirect beam exposure. Direct beam exposure is one of the possible sources. And the other one is diffuse reflections. It's an object that's not reflective or not very reflective, but you still have some exposure. And specular reflection is specular meaning like mirror, like a spectacle. Something that can really reflect the light quite a bit. And since a lot of times when you're doing physical experiments with lasers, you're depending on the use of mirrors. If they're displaced or moved or something like that, you can wind up exposing people inadvertently that way. Various kinds of eye damage. Again, nominal hazard zone is the distance that you need to be away from that in order to not to be outside of the range that you won't be exposed at the level that might be a problem. Okay, so some of the properties of this is, well, I say they're coherent, they're very narrow. There is a certain, they're not all perfectly directional. So there is a certain amount of spread or divergence that goes on, and the initial beam is a certain size as well. So all of these combine to give you the distance. The R means R is a radius. So it's in other words, as if the source is here and the R is the distance from that source in any direction, even though we know it's only pointing in one direction. Okay, so R is the distance that you have to be at to be outside of this hazardous zone. Okay, and that's going to be the impact on that is going to be the power, the amount of watts that this generates, the maximum permissible exposure limit. In other words, how far away do you have to be before you're that low? Pi and 4 pi involves like this idea of an area of a circle. The beam divergence, that what is that, psi? That's psi, right? Is that what that symbol is? Or phi? That's psi or phi? That's phi, right? That's phi, right? So phi is beam divergence in radians. In other words, instead of degrees, it's radians. That's unitless, by the way. Initial diameter of the beam in centimeters is A, right? So that's A squared, that's in centimeters. So we have an idea what we're going to be working with here in order to figure out what R is. Okay, so calculate the nominal hazard zone for a doctor using 100 watt YAG, yttrium aluminum garnet. That's what that is. 1.064 micrometer. Laser with, why am I having problems with that? Micrometer? I got that right? Micrometer, yeah, because it's laser. For some reason, it sounds wrong to me. Laser with a beam divergence of 2 milliradians, and that's how it's diverging. That's how it's spreading apart. And an exit beam diameter of 0.2 centimeters. That's the size of the beam coming out of the laser. Assume a worst case direct exposure over 8 hours. Okay, so first, look up for this particular type of laser. Okay, this is the wavelength, and this is the maximum potential exposure level. 5.1 watts over 10 seconds, 5.1 watts times 10 to the minus third. Okay, so did they use that 1.6? No, they used for 30,000 seconds. Oh, it's an 8-hour exposure, 30,000 seconds. 1.6 times 10 to the third minus third. So they would lower than this one because this is a shorter exposure. It can afford to be higher, right? So it's 1.6 times 10 to the minus third is the exposure. So what do we have? We have 1 over radiant power, and excuse me, 1 over the beam divergence, which is 2 times 10 to the minus third radians. No units there, right? 4 times the beam divergence, excuse me, 4 times the radiant power, which was 100 watts, 4 times 100 watts, over pi times, and this is the maximum exposure level, right? That's EL, exposure limit, minus the initial diameter of the beam, which was 0.2 centimeters squared. So what's going to happen here? Radians we don't have to worry about. Watts cancel out. We get centimeters squared. This is centimeters squared. We find the square, whoops. Let's see, centimeters squared. Centimeters squared here. We're subtracting this from this. This is centimeters squared. Take the square root. The units are centimeters. Watts cancel out. So the answer is in centimeters. And the total is 141.04. So I would have just answered this as 400. I would have called it 410 meters. Is the distance that you would have to be from this to have to not exceed, to have a location where you're far enough away that you're outside of the point where if you stared at it for 8 hours that you wouldn't have an exposure problem. So that's 4,000 meters. What's that, like a mile and a half or something like that? 1,500 meters is what? Is like 3,000 feet. And yeah, it's probably like a mile and a half or so. Based on calculation, based on that calculation, we're not going to protect ourselves by working with the laser a mile and a half away. So we're going to need eye protection. Okay, so what kind of eye protection are we going to need? Okay, so we're going to need some sort of filters. Okay, we're going to need some sort of filters. So now we go back to our first formula. Our lenses, what kind of filters are we going to use that will protect us from this device? Okay, so the initial power, the final amount of exposure that we want, the MPE, the maximum potential exposure, is 1.6 times 10 to the minus third from that chart for 3,000 seconds. In other words, an 8-hour day. So that goes on the bottom here. And on the top goes the laser, the power of the laser, which is 100 watts. We need a surface area. Okay, this is going to be that we're going to be exposed to. So what we're going to do is we're going to assume that our exposure is the size of our pupil, right? So that's going to be 100 watts per 7 millimeters. Okay, so the size of our pupil is 0.7. The diameter of our pupil is 0.7. We convert that into centimeters squared. It becomes pi r squared, right? Or pi d pi r squared over 4 is equal to 0.348. That's the area of our pupil, right? So we have 100 watts over that area is 260 watts per centimeter squared. That's how much power we have over that area. So that goes on top, and on the bottom goes our maximum exposure. So we need a protective lenses with an optical density of 5.2, logarithm of the result of that number. Okay, and again, these all cancel out. So it's unitless, basically. Okay. All right. So, and where would we get that? We go online. We go look for suitable glasses that will give us that protection factor for a YAG type laser. Okay, distance to far field. Now, remember we talked about that we could be dealing with either near field radiation or far field radiation. When we're dealing with near field radiation, we have to worry about the magnetic field and the electrical field, measure them separately. But if we're working with far field, high frequency and distance, sufficient distance, based on either having very short wavelengths or very large distance, if we can deal with far field, then it simplifies things. We only have to worry about the electromagnetic field. So how do we know if we're in the far field area? Okay, well, it's equal to the R, the distance for whether or not we can apply to far field formulas is equal to pi times the diameter of the antenna, if we're dealing with an antenna, squared, over 8 times the wavelength of the radiation, the wavelength that you're broadcasting from that antenna. So, and these are the two formulas. So if you're generating, calculate power density at a distance of 2,000 centimeters away from a 25 centimeter microwave, 25 centimeter microwave wavelength microwave source. The antenna diameter is 10 centimeters, has a power output of 2.5 times 10 to the 6th milliwatts. That doesn't sound that big to me. Not a very big radio station. Is the power density above the threshold limit when you're 2,000 centimeters away? In other words, if you're a worker working at that broadcasting center and you have to say work on the same roof or something like that. Okay, it's 2,000 centimeters, far enough away that you're below the TLV. Okay, so we apply for, first thing we got to do is apply the first formula to decide whether it's far field or near field. Trust me, it's going to come out far field. In fact, here's the far field. The far field is, in other words, the changeover from near field to far field for this frequency is 1.5 centimeters. We're at 2,000 centimeters. So we're going to apply the far field formulas. The power density using the far field formulas is equal to, let me go back and give you these units. Okay.
It's more than 2 wavelengths. That's what it's far field.
Right. Yeah. And so this is a very high frequency, right? This is 25 centimeter wavelength, right? So
That's how you would know to use that one.
yeah. Actually, because it would be based on let's see, R. That's a good point, because here it's based on it being 1.5 centimeters. But yeah, why wouldn't it just be 25 centimeters? I'll have to check that out. Okay, that's a good point. P is the average power outputs in milliwatts. Okay, we have that from the problem here, 2.5 10 to the minus 6th. The diameter of the antenna, I think it said it was 10 centimeters. The wavelength in centimeters, which is 25, and R, the distance from the antenna, okay, which is 2,000 centimeters. Okay, so when we calculate that, we wind up with, at 2,000 centimeters, the energy level is 0.078 microwatts per centimeter squared. We got to change that into watts per centimeter squared, because that's how our tables are notated. So if I go here, if we are at, what was the wavelength? I forget what the wavelength was. 25 centimeters. I have to convert that into frequency. But whatever it was a very high frequency, right? I don't have time to do the conversion right now. It's very high frequency. So if we're up, this is a particularly sensitive area. You can see this is kind of crossover where your exposure is particularly sensitive. In other words, the maximum, the magnetic field strength is and power density levels that you want to not be exposed to are lower in this range than they are in other ranges. You notice the magnetic field strength has become irrelevant here. So if you go up, say from up here, then we need to be under somewhere between 10 and 100 watts, based on what this, if I actually calculated the frequency now based on the wavelength, we would have to be between 10 and 100 watts per meter squared. If I go back, what do we find? We said it was certainly under 10 watts per meter squared. So at 2,000 centimeters away from the antenna, the worker is not exceeding the threshold limit value. Okay, so you got that homework assignment. So the homework assignment, for starters, you have for each one of those problems very similar to these. For each one of those problems, you have a version of it that you could just start from scratch and say, geez, I'm gonna go on my own and just do it, right? And go back to the PowerPoints and get the formulas and stuff. There's the other version that if you get stumped, you can go and use, and it'll give you the actual formulas and tables that you need to solve the problems. Okay, and if we're really stuck, we'll do videos on this problem solutions and stuff like that. And I welcome you guys to do your own videos and send them to me. Right? A lot of people like the ones when I did it for assignment 2 or 3 or whatever. You know, a lot of people have felt that helped them out quite a bit. But the downside is I don't want to put them up and then you have no incentive to do the problem. You just watch the video and put the number in. You know, so yeah, I want to give you some time to work on it. You know, so I made the due date on this. I think I made it like the same as either December 1st or the day before our next class, which is like December 3rd or something like that. December 3rd is fine. It doesn't have a physical due date. In other words, it will accept your submissions. And unlike the exams, you can go back and redo these homeworks anytime you want. Okay. The only thing I ask is that in exchange for that, you do at least one submission before the due date. In other words, you submit a homework before the due date, and that qualifies you to go back anytime you want and redo it for a higher grade. Okay. That's it for tonight. But it's actually pretty interesting stuff, right? Okay. How about you guys online? You guys are all okay there? Any questions? Micron. Yeah, that's true. Micrometer. It's micron. It's a micron. Thank you very much. You know, I knew there's something wrong with that. I just could not think of what to call it. Take care, guys. Good night. Thank you, Robbie.